Sun's red giant phase. Red giant will transform the sun into something almost unrecognizable within the next 1 to 1.5 billion years. As hydrogen inside the core runs out, gravity will begin crushing the center inward, while the outer layers swell outward to nearly 100 times the sun's current size. Long before the surface actually reaches Earth's orbit, the planet will already become unlivable. Temperatures will rise high enough to trigger a runaway greenhouse effect similar to Venus. Oceans will evaporate into the atmosphere. Water vapor will trap even more heat, and the skies will turn into dense clouds of superheated steam. Rocks on the surface may eventually melt. The sun's brightness during this period could become thousands of times stronger than today. Even microbes buried deep underground would struggle to survive. By the time the outer layers fully expand, Earth may either be swallowed entirely or left as a scorched, dead world orbiting inside a glowing stellar furnace. This is not a rare disaster, but the normal aging process of stars across the universe. Milky Way collision. Andromeda galaxy is already racing toward the Milky Way at nearly 155 miles per second, and the collision has already become unavoidable. Around 4 billion years from now, the two galaxies will begin their first close pass, stretching each other with enormous gravitational forces. Stars themselves probably will not collide because the distances between them are massive, but the structure of both galaxies will be violently distorted. Huge streams of stars will arc across space like glowing rivers. Over the next few billion years, repeated passes will eventually merge both galaxies into one giant elliptical galaxy, often nicknamed Milky Way. During this process, the solar system may get thrown much farther from the galactic center into a quieter outer orbit. The night sky would become completely alien. Andromeda could appear larger than the moon long before the merger fully begins, eventually dominating the sky with billions of visible stars and giant clouds of glowing gas. This kind of galactic merger is extremely common in the universe and is one of the main ways giant galaxies grow over cosmic time. Sun's white dwarf death. White dwarf marks the final stage of the sun's life after the red giant phase ends. Once the outer layers are expelled into space, the remaining core will collapse into an object roughly the size of Earth, but containing about half the sun's original mass. A single teaspoon of white dwarf material would weigh several tons because the atoms inside are crushed together under extreme pressure. Unlike normal stars, the white dwarf will no longer produce energy through fusion. It will simply radiate leftover heat into space for billions or even trillions of years. The glowing shell of gas surrounding it will briefly form a planetary nebula, creating one of the most beautiful structures in astronomy before fading away. By this stage, Earth will almost certainly no longer exist, either vaporized during the red giant expansion or stripped into lifeless debris. Nearly 99% of all stars in the universe are expected to end this way. Galactic center, supermassive black hole growth. Sagittarius A star currently sits at the center of the Milky Way with a mass equal to around 4 million suns. But over the next trillion years, it will continue growing by consuming stars, gas clouds, and smaller black holes. Every time an object falls too close, gravity stretches it into streams of superheated matter that spiral inward at near light speed. These accretion disks can become brighter than entire galaxies, releasing enormous bursts of radiation. As galaxy mergers continue across cosmic history, Sagittarius A star may eventually combine with other supermassive black holes, increasing its size dramatically. The collision between black holes would release gravitational waves so powerful they could ripple across millions of light years. Although Earth would be long gone by this era, the galactic center itself could become far more active and violent than it is today. Astronomers believe many ancient quasars seen in the distant universe were powered by exactly this process, where feeding supermassive black holes turned galactic cores into some of the brightest objects ever observed. Star formation stops. Star formation will eventually come to an end around 100 trillion years from now. Galaxies today still contain massive clouds of hydrogen gas that collapse under gravity to create new stars, but this fuel supply is finite. Over unimaginable spans of time, most of the usable gas will either be locked inside dead stars, ejected into intergalactic space, or consumed entirely. Without fresh hydrogen clouds, galaxies will slowly stop producing new suns. The bright blue stars that dominate active galaxies today will disappear first because they burn through fuel quickly. Only small red dwarf stars, capable of surviving for trillions of years, will continue glowing faintly in the darkness. Eventually, even those long-lived stars will die out one by one. The universe during this era will look dramatically different from today's vibrant cosmos. Spiral galaxies filled with glowing nebulae will vanish, replaced by dim collections of stellar corpses drifting through cold, empty space. This marks the end of the stelliferous era, the age where stars define the universe. Black hole era? Hawking radiation predicts that black holes are not completely eternal. During the so-called black hole era, stretching from roughly 100 trillion to 10 duodecillion years and beyond, almost everything left in the universe will revolve around black holes. Dead stars, white dwarfs, neutron stars, and planets may slowly spiral into them through gravitational interactions. Yet even black holes themselves will gradually lose lose mass through quantum effects near the event horizon. Tiny particles will leak away as radiation, causing the black holes to evaporate incredibly slowly. A stellar mass black hole could take far longer than the current age of the universe to disappear, while supermassive black holes may survive for 10 to the power of 100 years or more before finally exploding in faint bursts of energy. During this period, the universe will become almost completely dark. No stars will remain, no galaxies will shine. The only detectable events may be occasional flashes from dying black holes fading into a nearly featureless cosmic void. Heat death. Heat death of the universe describes the possible final condition of the cosmos, where every usable form of energy has been exhausted. Over unimaginable lengths of time, stars die, black holes evaporate, and matter itself may slowly decay into subatomic particles. Temperature differences, which drive all physical processes, gradually disappear until the universe reaches maximum entropy. At that stage, no engines can run, no stars can ignite, and no complex structures can form. Space would become a nearly uniform sea of low-energy particles spread across enormous distances. Even light would redshift into wavelengths so stretched that the universe would appear completely dark. Motion could still exist at microscopic levels, but meaningful activity would effectively end forever. Some models suggest this state may arrive after around 10 to the power of 100 years or even longer, a timescale so extreme that human civilization's entire history becomes smaller than a single blink compared to the lifetime of the cosmos.